Hello student, today I am going to teach you about the NP completeness. What is actually NP completeness? Because till now we have studied in the problem that were very easy to solve, such as such problem can be solved quickly in close to linear time, or at least the time that is some polynomial of the input size, like the n square, n log n, n o n plus b, or o n q in the worst case. And all these kinds of problems that we have studied can be easily solved in some polynomial of the time of the input n. But now there is a kind of problem that are type of bad news for us, that there are many important problems that cannot be solved that much quickly, and they take a very variable amount of times. NP complete problems really are those problems which cannot be solved in the polynomial times. Here, uh, if they cannot be solved in polynomial time, and they are solved using the different kinds of approach rather than a simple algorithm that we have studied, some of them are solved using the heuristics, means come up with a method for solving a reasonable fraction of common cases, means uh, some of the proportion of them can be solved with the help of the some previous solved problems, and in this way we can break those parts. And while some other problems which are NP complete can be solved using the approximation, and you shall study later that there are approximation algorithms, and the heuristic means the randomized algorithm. You shall study the case of the randomized algorithm and the approximation algorithm dealing with these categories. In approximation we come up with the solution that you can prove that is not the exact solution, but that is very close to the right solution. Means you are not declaring that this one is the best solution, but you are providing a solution that is very much close to the best solution. And in heuristic, you solve the problem using some random sequence that you guess that these could be the results. And otherwise, and the other portion, there are also problems of NP problems, complete problems that take exponential times. Means if you really have to solve the problem exactly, and you want to find out the for finding out the better solution, then you take the exponential amount of time. Means that is very huge amount of time. Which kinds of problems comes under this NP complete problems criteria? There are problems that are called the decisions problem and optimizations problem. There are problems which have been characterized into the decision problems and optimization problems, which comes under this category. Decision problems are the problems which are giving an input and a question and a problem, input and a problem or statement determine whether the input answer is yes or no. If the suppose a number is Fibonacci, and suppose you have the problem is to find out that what is the method of finding out the Fibonacci problem. Suppose that this is the NP complete problem, then on giving an input, this algorithm should give you answer that yes, it is Fibonacci number, or no, this is not a Fibonacci number. Then this is called the decision making uh, algorithm that declare that whether the number is Fibonacci or not. I have just like this kind of decision can be taken in a number of cases. So in the two broad categories, one type of problem that comes under the category of NP problems are decision problem, and another one is the optimization problem, with which you are well familiar of, like the finding out the shortest path in the graph. And here you can not um, find the shortest path with the shortest number of edges, but uh, it is very difficult to find out the shortest path every time in unweighted directed graph if it is when the graph become complicated. So these problems also goes under the category of the NP complete problem. And algorithm versus problem complexity. The complexity of the Computation is some measure of how difficult it is to perform the computation. The complexity of the computation problem or task is the complexity of the algorithm with the lowest order of growth of complexity for solving that problem or performing that task. Means the complexity of a task is the complexity of the algorithm. Suppose for solving a problem, particular task, you design a corresponding algorithm, and the maximum amount of time the algorithm or that algorithm will take to run will be the complexity of that algorithm. On the basis of the complexity, problems are classified from easy to hard, and NP complete is one such criteria. Besides this, on the basis of the complexity, the problem are divided into certain categories. The one that are P problems are called the traceable problems. The problem that are not in P are called unsolvable problem or intraceable problem. P problems are solvable problem that can be not in P. They can be solved in reasonable time only for a small input or cannot be solved at all. There are some problems which can be solved for a small number of small size input but cannot be solved for large size input. That kind of problem will not be considered as a polynomial problems. Uh, First of all, can we say that the null polynomial algorithm always are always are the worst algorithm rather than the polynomial algorithm? Because some algorithm may have the polynomial problem, he may have the complexity n raised to the power 1 million. That is technically traceable but impossible, because if it is taking so much time, then it is not practically feasible. While in the case of non-polynomial problem like n raised to the power log n is technically traceable and easy. So we cannot say by just saying that the polynomial and non-polynomial that which one is better, because it will depend on the particular problem. Uh, we all know that if a problem is solvable, then that can be implemented on the Turing machine. And if we cannot, for every solvable machine, there is a Turing machine, and if we cannot design a Turing machine problem, then that problem is considered to be unsolvable problem. Example of some problem that are very difficult to solve when the number of inputs increases. That can be they may be solved for the smaller inputs, but when the size of the inputs increases, they become very difficult to manage. Some of the problems are Hamiltonian path. Like in Hamiltonian path, we have to find a path that passes through the each vertex exactly once, and this is very easy problem, and we solve that problem. But this problem becomes very intraceable when the number of input increases. And similarly, the traveling salesman problems, when the postman travels through all the nodes and moves back to the initial node, are called the traveling salesman problems. And in it, we basically find out the Hamiltonian path. And in this problem, we add on the weights that we have covered. So this is the problem that is also very difficult when the size of the input increases very much. So these type of a problem which are very difficult to handle can be divided into the three categories. The first one was the polynomial problem that can be easily solvable, and that runs in the some polynomial of input size, and that are traceable. Traceable means that can be solved, but there is another category that are intraceable problems, and in this intraceable problems we are again dividing the problems into three classes. These classes are NP problem, NP complete problem, and NP hard problems. So first of all, the NP problem. Class NP consists of the problem that can be solved by NP problems, and they are verifiable in polynomial times. Means the algorithm that solve them is not polynomial of P, but these problems can be verified in polynomial amount of time, because suppose means they can be verified but they cannot be solved in polynomial time. This is the difference. That means if the solution is given, then you can check that, verify that whether the solution is correct or not, but for solving the problem you take non-polynomial time. Means here we have given a certificate of solution, and which gives the answer in terms of yes and no, that the problem is answer is the solution is acceptable or not. The NP does not means the non-polynomial problems. You cannot simply say that it is not non-polynomial problem. That is this is the point at which everybody get confused. For example, the Hamiltonian cycle problems. We have to find out the simple cycle that contains the each vertex in V. And here, for the given graph, we are creating a cycle that cover all the vertices. And for the following graph, the second one is not a Hamiltonian, because in the second case, we have to at least pass through the mid node at the center twice to cover all the vertices. So can we say that it is still not very much clear that whether the P is equals to NP or not, or P is subset of NP, because this is the problem that is still not solved. Has not been solved. So NP problem is a part of the NP problem, but we are not sure that our P's are subset of NP or P is equals to NP. So most scientists believe that P is subset of NP. NP completeness problems are defined as the hardest problem in the case of NP. Among the intraceable problem, NP complete problems are considered to be the toughest problems, and most problems turn out to be either P or NP complete. So, for the problem, the technique that is used to solve this problem is the reduction technique. If there are two problems A and B, we see that the A is polynomially reducible to B if A is less than the polynomial of B. There exists a function f that converts the input of A to the input of B in polynomial time. Two problems are said to be reducible to each other if problem A input, if there is a function that can convert input for algorithm A into input of our algorithm B in polynomial amount of time, then that problems are said to be the reducible to each other. And we shall say, suppose we are converting the input of A into input of B in polynomial time, then we can say that A is polynomially reducible to the B. The NP complete problem. A problem is NP complete if the problem is a NP problem and problem B is any problem that is in non-polynomial is the less than or equals to the of the polynomial of B. Means if B satisfies only property 2, then we say that B is a NP hard problem, and no polynomial time algorithm has been discovered for the NP problem, complete problem. And no one has ever proven also that no polynomial time algorithm can exist for any NP complete problem. From this diagram, we can show you that how the problem A inputs alpha is converted into problem B input beta using a function f, and after converting this, we can say that the problems A input can be converted into the problem B, and we can get the answer similarly using the problem A algorithm. And if A is less than the polynomial of B and P is a polynomial problem, then A would also be a polynomial problem. And likewise, if A is the less than equals to B polynomials, then if A is not polynomial, then B would not also be a polynomial problem. Proving polynomial time. Um, In this case, if we have an algorithm for the problem B, then we can use the answer of B for answer of A, but just by converting the input of algorithm A alpha by using a function f that converts the alpha into beta, that is the input for the algorithm B. It means for algorithm A, we do not need to redesign the algorithm. With just by converting the input corresponding to algorithm A to the input corresponding to the algorithm B, we can use the algorithm for the B to solve the algorithm to create the algorithm for problem A. And suppose if we want to prove that the given problem is NP complete, so we have to prove that if A is NP complete and A is less than the polynomial of B, and B is an NP hard problem. And in addition, if B is NP and B is belongs to NP and B is NP complete problem. Uh, for example, suppose B will assume that B is a polynomial problem. Since A is the less than polynomial of B, so A would be a polynomial problem. So this will be a contradiction. It means that first statement that was B is subset of NP is wrong, and is in this case is if the first condition is not satisfied, then B is the NP hard problem. And if B is NP hard problem, so proven that the B is NP. And now a randomly generated string can be checked in polynomial time to determine if it presents a solutions. So show that one known NP complete problem can be transformed to B in polynomial time. So no need to check all the NP complete problem are reducible to B, and we can say that that is NP hard problem. And the second theorem is if any NP complete problem can be solved in polynomial time, then P is equals to NP. Suppose the shortest path algorithm, in which we find out the shortest path from the source to all other vertex, and with polynomial time equals to O of VE, and the longest simple path, find the longest path from a source to all other path, is NP complete problem. Some of the problems we are studying that while the finding out the longest path is NP complete problem. And similarly, the Euler too. If a graph is a connected directed graph, find a cycle that traverses each vertex of the G exactly once. Like the Hamiltonian will take the polynomial time O of E, while the Hamiltonian cycle, finding a Hamiltonian cycle connected directed graph, and find the cycle that each vertex of the graph exactly one is NP complete problem. That traverse each edge is the polynomial problem, but that cover each vertex is a NP complete problem. Satisfiability problem. Given a logical expression, we have to find out the assignment of the value to the variable xi that causes the function to satisfy. This is called the satisfiability problem. Satisfiability problem was the first problem shown to be the NP complete problem. The CFN is a special case of the circuit satisfiability of the satisfiability problem. Here the function is written in form of the CNF form. We have conjective normal forms, and each closure contains only OR of the variable and their complements. Here in the function, each clause contains only the OR functions. While converting the functions into the CNF form, uh, contain CNF form, the subcase of CNF problem is like this. Here, each clause has only OR gates inside it. The 3 CNF is the NP-complete problem, but 2 CNF problem is the polynomial problem, the click problem. In undirect, if there is an undirected graph, a subset of vertices in V all connected to each other by edges, forming a complete graph. The size of the graph, number of vertices, size of the click, the number of vertices it contains. The size of the click would be the number of vertices it contains, and the click is the subset of the vertices in V which are all connected to each other by edges in E. So optimization problem to find out the click of maximum size is the does G have a click of size G? These are the two problems. Click verifier. So these are the problem that we have to find out the solution. This also comes under the case of NP complete, because 3 CNF problem is the less than the polynomial of click problem. Construct a graph such that the function is satisfiable only if G has the click of size K. Now we shall discuss the NP namings conventions. The NP complete problem means the problem that are complete in NP, that is the most difficult to solve in the NP problem. NP hard stand for at least as hard as NP, means the NP complete problems are the most difficult one, but the NP hard problem are at least as hard as NP, but not okay. NP is stand for at most as hard as NP. At most, they are at most. These are two words you keep in mind. The NP hard are the at least as hard as NP, and NP easy stand for at most as hard as NP. And NP equivalent means equally difficult as NP equivalent. Example of NP complete and NP hard problems. The example of NP complete problem is the Hamiltonian path problem, in which find a path that passes. We have to find a path that passes through each vertex exactly once. This is the NP complete problem. While the traveling salesman problem, in which we have to travel through each vertex by traveling the minimum distance, is the NP hard problem. Is the NP hard problem. So that's all about the NP complete problem, and thank you.